Hi, and welcome to mini lecture 1 for week 11 of the Quantum Universe for Educators. In this lecture, I'm going to describe one very important consequence of quantum tunneling, the main consequence of quantum mechanics that we'll be looking at this week. And this is one consequence that you really want to go and tell anyone who doesn't realize how important quantum physics is. To put it bluntly, if quantum mechanics didn't work, then the sun and every other star would not shine, and no life would ever have come into existence. So let's quickly review what quantum tunneling is. So if you take a baseball and you're sat at the bottom of Mount Everest, then the problem of throwing the baseball over Mount Everest simply comes down to a question of energy. Can you give it enough kinetic energy to get it over the potential energy barrier that is Mount Everest? Okay, you have to give it enough energy that you can get it over this height, this energy barrier, which has a height in units of energy that's equal to mgh, just the gravitational potential energy at the top of Mount Everest, where m is the mass of the baseball and h is the height of Mount Everest, g is the gravitational acceleration, 10 meters per second squared. Now, we all know that we aren't ever going to come close to be able to give the baseball enough kinetic energy to get it over Mount Everest, no matter how hard we throw it. It's simply not going to work. But the equivalent situation in the quantum world is different, because in the quantum world, things that we think of as particles like electrons and protons are not particles. They are described by a wave function, and wave functions are extended over a wide region of space. They're not localized to a single point. So let's look at the equivalent situation. Here we have a potential energy barrier again. So this is like our Mount Everest, this tall barrier that our particle wants to get over. And let's say our particle starts out over here on the left-hand side of this diagram. So we've made some measurement and we've determined that the particle has started out somewhere over here. We don't even necessarily have to be specific about where. Now, that particle is described by a wave function, which is shown by the red and blue continuous wavy line here. If E is the kinetic energy of the particle and V is the potential energy, then in the regions to the left and the right of the barrier, the particle has a greater kinetic energy than the potential energy. But let's suppose that this barrier here has a potential energy that is higher than the kinetic energy. Okay, just like Mount Everest, the potential energy required to get over Mount Everest is higher than the kinetic energy that we could possibly put on that baseball. Now, if you solve the Schrödinger equation for the particle, and we will get to the point in a couple of weeks where we can do something like this for simple situations, then you'll find that the solution is this wave function here. So it's extended throughout space, and it has its highest amplitude on the left-hand side where it started out. But it still has a small amplitude over here on the right-hand side, the other side of the barrier. Now, the square amplitude of the wave function is the probability of finding the particle at a particular location in space. So although most of the probability is on the left-hand side, so we are most likely to find our particle on the left-hand side, there is a small probability that we will find it on the right-hand side. In other words, there's a small probability that when we make a measurement of where this particle is, it will appear to have got through this barrier that it didn't have enough energy to get through. Notice that it hasn't lost any energy over on the right-hand side, because the energy of the particle is not determined by its amplitude. Its amplitude tells you just the probability of finding the particle in a particular place. It is the wavelength of the wave function that tells you how much energy the particle has, and the wavelength on the right-hand side is the same as on the left-hand side. So the particle is able to get through this barrier that has a much higher energy than it has, and it's not only able to get through to the other side, it's able to get through with all the energy that it had to start with. So this is quantum tunneling. So let's talk about one of the most important places where quantum tunneling comes into effect, and that is in stars. So let's take the sun, since that is the star that is up close to us. Now, stars get their energy from nuclear fusion that is occurring in their cores. So the light and heat that comes from the sun is generated deep in the heart of the sun by nuclear fusion. In the sun, the main nuclear fusion reaction is the so-called PP reaction, which is displayed here. And we don't need to go into the details. What basically happens is that at the start of the PP reaction, two hydrogen nuclei, which are protons, so two protons, come together and fuse to form a neutron and a proton, which fuses with another proton to form helium-3 nucleus, two protons and a neutron, and it fuses with another helium-3 nucleus to give you helium-4 plus two protons, which then are able to go off and start the reaction again. So there is a self-sustaining cycle here in which protons fuse together to form helium, and this process releases a lot of energy, and is that energy that powers the sun and gives the light and heat to the Earth and makes life possible on the Earth. The thing is, the very start of this reaction requires two positively charged protons coming together and fusing. And that means they have to get close enough to fuse. They have to overcome the electrostatic repulsion. They are two positive charges, and like charges repel. And you might ask, how much energy do they need to get close enough to fuse? Well, if you plot the potential energy between two protons as a function of their separation r, so r is simply the distance between the two protons, then as they get closer and closer together, the potential energy starts increasing rapidly. So you have to put in more energy to get these protons closer together, and that's what we expect because they are repelling each other. So you have to do work to push these protons together. Once you get them close enough, however, another force of nature, the nuclear force, the strong nuclear force, takes over, and that is attractive. And the two protons then attract each other with a force that is stronger than the repulsive electrostatic force that is forcing them apart. And then they come together and fuse. So the trick is to get them close enough that this attractive nuclear potential takes over and allows them to fuse. So they have to get enough energy to overcome this potential energy barrier. So this is like the situation with a baseball and Mount Everest. And it is actually quite similar to this in terms of energetics. If you do the calculation, you find that the kinetic energy of protons in the heart of our sun is nowhere near enough to get them over this hump, this potential barrier here. Just like the kinetic energy that we can give a baseball is nowhere near enough to get it over the top of Mount Everest. Now, in this week's assignment, you'll actually test this out, because the kinetic energy of the protons in the heart of the sun is actually related to the temperature of the heart of the sun, of the core of the sun. The kinetic energy of a single proton is 3/2 kBt, where T is the temperature in Kelvin and K sub B is Boltzmann's constant. So that is the kinetic energy that the protons have. The height of this barrier is given by Coulomb's law. The electric potential energy between these two protons is equal to Coulomb's constant, Kc, times the square of the charge of the proton divided by the distance between the protons. And the distance between the protons at this point here is about 5 × 10⁻⁻15 meters. That's how close they have to get before the nuclear potential takes over. So in the assignment, you'll plug in the numbers and you'll confirm that the kinetic energy of the protons is nowhere near enough to get over the potential energy barrier between them. This is the result that you will find. So it's worth being particularly dramatic about this. Classically, the sun just doesn't work, and every star in the night sky that you see will never have got going. It will never have shone a single photon of light. Life on Earth would never have even begun. The very existence of life we owe to quantum mechanics. Because in quantum mechanics, this is what is going on. The proton wave function far away from the other proton looks like the picture that we saw earlier. The Coulomb barrier is now the potential energy barrier here. And although the proton has nowhere near enough energy to get over the Coulomb barrier, in quantum mechanics it's described by a wave function, and part of that wave function is the other side of the barrier where the proton can fuse with the other proton. So there is a small but non-zero probability that the proton will be found in the region close enough to fuse with the other proton. And that small probability is enough to generate enough energy for the sun to have shone for 5 billion years, and it will provide enough energy for the sun to shine for 5 billion more years.